3 minutes to start. Everybody copy this down if they're going to. All right? Did you decode it yet? Really? Don't tell anybody what the secret is. You can tell them what the message is, but don't tell them how to decode it. You got to get it on your own. So this is the point before the talk where I apologize. Because those of you who have come to my talks in the past, you know that I have a particular slide that I love, the slide format that I love, and it's this. Sadly, due to some unforeseen creation circumstances, this is the only slide that was able to stay like this for this presentation. But it'll be back in the next one. Stupid white background pictures. All right, thank you so much for coming out today. Anybody coming to see a talk entitled Shh? And not walking in saying, it is welcome here. I appreciate you very, very much, and your faith in at least being interesting and entertaining is wonderful. Thank you so much. So the title of this talk is actually PowerPC style. And I won't try to dance, partly because I sprained my ankle and it would not be pretty. We're going to talk a little bit about PowerPC. Anybody heard of PowerPC? Anybody under 40 heard of PowerPC? Good. So, in typical Atlas fashion, I'm going to try to have a lot of fun, technical stuff. If you've never heard of PowerPC, welcome to the 20th century. However, I will probably surprise most of you. So who am I? My name is Atlas of Doom. Of Doom got thrown in there because some forms require a last name. I have been blessed to be a part of some of the coolest projects that I can even imagine, including breaking out of VMware, hacking on PowerGrid. I got to write a tool called RFCat, some of you have probably heard of. For the last several years, I've been hacking and breaking into vehicles, and I can't get over playing Capture the Flag, even though I feel like about PowerPC. Well, first of all, because it was really cool chipset back in the 90s that died off. Oh, no, wait. PowerPC is dead, right? Let me hear you say it. PowerPC is dead. It's malcontent. Disruptor. Long live PowerPC. So PowerPC is everywhere. A few years ago, when I first ran into it in a professional project, I'm going, I thought this died before Sun did. You guys heard of Spark, right? No. PowerPC lives on. In fact, we'll talk a little bit about history in a bit, because in my adult life, I've become a history buff, because history is not a bunch of dates and dead dudes and ladies. History is how the world works. So, I get really excited about how the world works and how it comes together, because this was a pain in the ass. Anybody who's ever read any documentation and tried to make sense of a PowerPC chip will resonate with PowerPC being a pain in the ass. It has a reason, and we'll talk about it in just a second. PowerPC can be found today shipping product in aerospace, in automotive and heavy trucking, in shipping and in maritime stuff. Did you know that a huge segment of IBM's current sales ship PowerPCs? Anybody heard of a P-series? All your AIX stuff has always loved the power. In fact, PowerPC got its start based on IBM's original power architecture. So hacking one of these systems can get you really interesting capabilities. And because your life and the life of your loved ones may depend on it, PowerPC may become very interesting to you. I know that it is for me. So we need to be able to protect these systems, because They're in your car. Typically in your brake controller. I mean, if you're going to have something fail on your car, probably not that one. That's not my first choice. So it turns out a few years ago when Grimm first started doing professional automotive exploitation, we were given a car and we had to hack a certain number of things in it. And we figured out a whole bunch of stuff. It was great. We were able to pull down firmware for all the different things. And we took the firmware and we were going, okay, this is ARM. This is Renaissance. This is no idea. Not a clue. And so we ended up rolling through different architectures into disassembler going, nope, nope, nope. Hey, that has some those are weird-ass instructions. Nope. Keep going, keep going. We failed in a 2-week period that we limited ourselves while doing other things. But we were like, at the end of this, we're going to cut it and take this other route. We ended up cutting and taking this other route only to figure out at the very end of the engagement, the disassemblers have a bug. The tooling that we were trying to use didn't make sense of the code because every one of them had a bug. IDA had a bug. OBSJump had a bug. Radare, well, let's not even go there. And Vivisect didn't support it, which is my favorite. So that got my brain spinning. We didn't actually confirm it until one of my guys, who I think is here today, Mitch Johnson. He's no longer my guy, but he's an awesome dude. He's like, OBSJump has this thing where the particular type of encoding that this firmware uses, because that's what I think this chip should be, it only turns on that, it only enables that if it's loading an ELF binary. You guys know what an ELF binary is, right? It's like, it's the Unixy way of storing binary executable code. So if we had a raw image of firmware, which is what we did, nothing. Could not get OBSJump or IDA or anything else to disassemble it. I don't know about you, I don't know how you like to learn architectures, but I like to learn architectures by writing a disassembler. Teaches me how the bits turn into assembly, and teaches me really interesting things like, hey, these 4 bytes look like this type of instruction, and this bunch of things figures out that kind of looks like this architecture, and believe it or not, that's been very successful for me so far. So some of the Grimm folks embarked on a journey to create a PowerPC disassembler for Vivisect. Why? Because I love Vivisect. But we'll talk more about the reasons in a minute, because it was a business decision. So that was the light-duty ABS module. We also found PowerPC on a very interesting heavy trucking ECM in a gig just after that one. So turns out PowerPC is playing into my life on a virtually daily basis when I'm doing the fun stuff. Yes, this is a 72 Datsun 240Z. There's not an ounce of PowerPC in there because it's not got a computer. I did that because, well, I work with these car companies and I didn't want to out anybody or make anybody uncomfortable. Done that. It's caused lawsuits. It's not a good thing. PowerPC is some crazy shit. So back in the day, back in the 90s, Apple, IBM, and Motorola formed the AIM collaboration, or the AIM project, where AIM, Apple, IBM, Motorola, they're like, you know, those Wintel guys, they're getting pretty tight. And it's limited to 32 bits when we really want to have a 64-bit architecture. Let's go make the next killer architecture. And it'll take over, we'll have Windows NT work on it, we'll have OS2 work on it. Yes, this is back then. So they created this architecture based on the IBM mini computer architecture, which supposedly is so much better than the Intel microcomputers. It's been around for 27 years. A few tidbits about it. It's a 32-bit fixed instruction set. What's that mean? It means every instruction is 4 bytes long. as opposed to Intel, where it could be 1 byte all the way up to 15 bytes in length. Or they could be actually making it bigger as we speak. So 32-bit fixed size instruction set, except they added in this nifty little thing called VLE, variable length encoding. Anybody heard of ARM thumb? ARM architecture? Just stick them up if you heard of ARM. All right, good. How many of you can understand why they invented thumb, aside from causing pain to reverse engineers? What's that? Power? Close. You're getting there. Give me something. Code density. Cheap is the word actually I was looking for. Code density means cheap. On little embedded things, you can fit a reduced instruction set thing to make a smaller piece of code so you can buy a smaller flash chip or EEPROM. Okay? It's the reason they created thumb. VLE is basically PowerPC's version of thumb. Variable length encoding says we're going to keep a bunch of 32-bit instructions because we kind of gotta, and we're going to make a whole bunch of 16-bit instructions so that we can have code density. The architecture that we were looking at for the ABS module was running pure VLE from the get-go. So, like, everything was either a 16 or a 32-bit instruction, and it caused all of our disassemblers to take a shit. It is big endian. There are a number of add-on modules that can give you a bunch of specialized registers, but generally speaking, PowerPC has 32-bit, or 32 general-purpose registers. Like in Intel, we've got RAX and RBX and RCX. Okay, there's like 16 of them. This one has 32, and then 32 floating point registers as well. One interesting tidbit that I found, I didn't realize right away, is that most chips for PowerPC, because PowerPC was supposed to be a full-blown, like, supercomputer type machine and a desktop and a server. So they have a boot assist module that looks through at different different physical addresses of firmware or disk to look for a particular sequence of bytes. And if it finds those particular sequence of bytes, it starts executing code from a pointer that follows those bytes. So, intro to reverse engineering PowerPC. You're very welcome. You can send checks to... Just kidding. Oh, and those sequence of bytes, it's called an RCHW. If you ever see RCHW, you'll just know, hey, that is a reset config half word. I just made your life that much better. Okay, digging in, trying to figure out how this thing works. Now, I've done a lot of architecture reverse engineering, particularly on embedded systems, so the idea of layered documentation is not new to me. So we dig in, okay, we've got this EREF. What the hell is an EREF? I have no idea, but I know that it is important for the code that I'm looking at, so I'm reading it. Oh, I then run into a Power ISA, an instruction set architecture reference manual. Okay, interesting. Then we've got this Altivec PIM, what? And VL, come on, where's the easy button? Turns out there really isn't an easy button because, and then we've got these implementations of chips documentations. But it turns out, because of the AIM Alliance, as they name themselves, realizing, oh shit, Wintel's not going away. We can't win this war. They kind of panicked and all went and did their own thing, because they all owned the intellectual property. Might as well make use of it, try to recoup some of our investment. So IBM continued to make now the P series, probably changed names again since I looked that up. Apple did you've heard of G3 and their G4 and their G5 processors? Back just before they switched to BSD on Intel, That was all their PowerPC stuff on the desktop. And of course, Motorola, what do? Well, they're an embedded chip company, right? Well, they do a bunch more than that. They spun off their embedded stuff and sold it to NXP. NXP still running and selling PowerPC chips to ECU manufacturers for automotive and heavy truck, embedded systems for aerospace. All of the stuff that I said early on, the stuff that can kill you, NXP is selling those chips like they're going out of style. You just never see it. The problem is, Apple wants to do their thing because Apple is the easy button of computing, right? Hey, I need it to be easy, fast, and beautiful. Well, IBM's like, this is going to be the next mainframe killer thingy. And NXP is going, better not draw over 2 amps. So they had very different directions that they're taking. And as you might suspect, when they're not working together, they do their own thing. In recent years, in the mid-aughts, in the early 2000s to mid-2000s, we see them coming together and putting together a unified documentation called the Power ISA with an open source community called power.org, or a nonprofit, power.org. And then they're finding out, oh shit, I wish we wouldn't have done that. I wish you wouldn't have done that. And so they're trying to merge these things together. But in 2013, we ended up with something somewhat cohesive. And in 2017, we came out with the Power ISA version 3. All right, history lesson over. Sorry to dwell so much. It caused me so much pain, I just needed to share the pain. Why did we build this for Vivisect? Why not Ghidra or IDA or whatever, Hopper? First of all, Vivisect, what is Vivisect? It's a very powerful binary analysis framework focused specifically on bug hunting. Let's go own some Ode. It has lightweight or heavyweight emulation capabilities built in, as well as a symbolic emulation engine. Anybody heard of symbolic analysis? Okay, stick them away high. You can own it, loud and proud. Okay, about 1/30 of you. That's fine. Symbolic analysis is where you take code and you translate each instruction into its symbolic effects. And then, one thing that's special about Vivisect is that you run those effects through a symbolic emulator, and it extrudes the state of the system in a very trackable way through an entire code path. Why do we care? Whatever, nerd. Because I like to write code that answers questions about code. Symbolic analysis and emulation together provide a very, very powerful platform for finding no-shit zero-day. Collaboration server built in, powerful graph library. If you get into symbolic analysis, you'll find graph theory is a lovely thing. It is open source. It runs virtually pure Python, except where it hooks into the OS to do debugging. But of course, you can't do pure Python and debugging. It doesn't work. And it's easily extended because it's pure Python. And it's open source. You look through, read the code, change whatever you want. It's got wrapped into it something called VDB, a vulnerability debugger. Again, debugging system focused on finding vulnerabilities. Anybody heard of the APT1 report? Really? The Mandiant APT1 report? Man, it's not been that long. Okay. It was the report that told the world in no uncertain terms with proof that China's been stealing intellectual property from the US to the tune of 10 million a day. Not many people.
Once you said it was I remember. I just forgot the name.
Got it. Okay, that makes sense to me. It was pretty epic because we had all assumed that it was working that way, but really, I'm my worst person here. I need to shut off my phone. I have thrown my phone against, So yes, this report basically made it so that congressmen had leverage to say, that's not okay. Before that, we just kind of all said, yeah, they're doing it, and we all know it. So the APT-1 report was based on an intelligence gathering and manipulation system, not manipulation, that sounds bad, intelligence digesting system. The interface actually was called Jarvis. And when you logged in, it said, good morning, Mr. Star. Anyway, it was based on a whole bunch of code. Vivisect was part of it. So they streamed all the things off of the internet, they parsed them, and did a lot of binary analysis, and Vivisect is at the core there. Again, the main reason is because I love it, and that's enough. But I thought I'd give you the other stuff. With Vivisect, I've built and maintained bug hunting tools, ROP gadget finders and auto generators for a chain, and other behavioral analysis modules. So, how do you start writing a disassembler in Python? We won't even get into why, again, because I love it, and Python, it just makes me happy. Turns out, writing a disassembler, it's not really that difficult. It is entirely too tedious and time-consuming for me to convey to you, but it's surprising how quickly you can come up with something of real value. It is also error-prone, so lots of testing and unit testing come into play. So writing a disassembler by scraping documentation, however, gets rid of a lot of the tedium, at least from the disassembler perspective. So what I did was I took the EREF doc manual, and they've got several different tables of how bits decode into instructions with fields and whatever in ASCII, and I scraped out one of the tables and wrote parsing code for that copy and paste. Sounds horrible. It's really ugly shit. I'm sorry, it is. But it was really powerful and saved me a ton of headache. Even had I put in the same amount of effort that I would have put in by writing all the tables, A, it's less error prone because I wrote it specifically against their data. And B, I felt a lot less drained at the end because I got to write logical code instead of tedium. So once we write, we end up spitting out tables that we can look up and do cool stuff with. We write some supporting code, including a disasm function that says, give me some bytes and I'll do something with them. A PowerPC opcode object. It's a Python thing, right? So we create a Python object that stores all the things about the opcode itself, including a list of operands. An operand. Anybody written assembly language? All right, good. Like half of you or more. That's wonderful. So in assembly language, you have the mnemonic, the word that tells you what it is, like a move, and then you have a couple comma delimited operands. So move from this thing to that thing. These things are called operands. So we start writing operand objects, and then the opcode object, and it just mirrors what the PowerPC needs, and it stores whatever it is. So because I wrote a tool that parsed out a bunch of junk, this is what I copied and pasted. And it's the beauty of Python. This variable equals three tick marks and then like just gobbledygook for forever. And then 3 more tick marks to end the string. And then I parse it out, and here's the parsing code. Parse this stuff out, okay, blah, 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 blah. Just, break it up into new lines and whatnot. And look for these things, because this means I'm on to another instruction. Blah, blah, blah. It can be ugly, but super powerful. And To date, I have not modified those tables by hand. When I found a bug, and yes, there are bugs in the documentation too, I'll go in and I'll fix the bug in the scraped portion and regenerate because I'm not ready to let go of that safety balloon just yet. But it can take a lot of stuff, a lot of code. This is not a lot of code, actually. I'm a lot of slides, I suppose, to describe it. And a piece of the table. So we break it down into little subcomponents so that we can easily search quickly instead of, what you never want to do when you're writing fast code is put in a list of everything that you have to hunt through from the beginning, even if it's the last thing in your list that you want to get to. So a nice dictionary lookup with the different segments, breaking it down into a bunch of tables that you then scroll through very quickly. And when you're doing disassembly, you need to write the code. You need to write the code such that it could run millions of times and not really cause you pain. All right, so our operand class is here. Here's an example of an assembly instruction. Move register R7 into R4. Whatever was in R7, put it into R4, the register R4. Cool. So we store all the information about the MR and any other special flags that might happen in the opcode. And then we store the information about each operand into an operand object. The operand object, because there are probably about 15 or 20 operand objects that I'm using, it knows how to render itself. So if it's a number 5, does that mean it's binary? It's got to be 101. Would that be the number 5? Would it be 0x5? What makes sense? And the operand object knows that just by context. It also, the operand object, knows how to get stuff from that operand and to write stuff to that operand. So if it's a register, it says, oh, grab the data in this register that we're storing, and when we're writing to it, put it back. So we've got some examples of operand classes, including storing, evaluating equality, normalizing, getting the data, get oper value, the thing that's in the register, or hey, if we're dereffing memory, the thing that actually goes and grabs the thing out of memory. Set oper value, same thing, the thing that puts the data into memory. Get oper adder. Ooh. So if it's a register, it just says none. There's no address because it's a register. But if it is a memory location, get oper adder points to, it actually returns the location in memory instead of the data value there. We have a render object, which is like the pretty thing for all the GUI magic. And then we have a repr function, not object, that prints it out if I just say print. And I do a lot of interactive disassembly and interactive Python, so the print stuff is important to me. Enter the unit tests. Okay, this is where you all groan. Unit tests are fun. Unit tests are your friends. Really? I'm selling you something. Turns out unit tests kind of suck. They're a little tedious. If anybody tells you otherwise, they're either on a better drug than you or they're full of shit. But the alternative is much worse. Unit tests. It's hard enough to write the thing right in the first place. It's harder to maintain it and fix all the bugs because you will write bugs. You'll interpret the documentation wrong, which is even worse. Like typos are one thing, but I had no idea that's actually what that meant. And as you maintain the project, you'll break shit that you didn't mean to and you don't even know it. So, unit tests are worth it. Even a hacker has to accept that. So, enter my good friend Aaron Cornelius, who hopefully he's here today, but if not, give him hell, because he agreed on his own time, like not work time, he agreed on his own time to help me out with this project. And he knows a lot more PowerPC than I do. But I will say, I wrote the disassembler. He wrote it like an entire disassembler to write unit tests. I have no idea what the hell that man thinks, but I love him for it. Because it was like he wrote an operating system. I'd say, hey, this unit test is weird here. He's like, oh, wait a second. And he changes his generation module and then recompiles. What the heck is that? Your code for unit tests is more complex than my code to actually do the thing. It's like, that's the way it should be. Thank you, Aaron. I very much appreciate it. So we started off with a bunch of code from other disassemblies like IDA and objdump. And we parsed them out, we normalized them, that's what Aaron did, and then spit them out into unit tests. And we found bugs in their disassemblies as well. It's always very fun to start using other tools to test your tools, because when they differ, don't assume that your tool's in error. Go back to the documentation. If the docs favor you, they've got a bug. And then we wrote some emulation tests. We're still writing emulation tests. There's no real easy way to make that happen automatically. So who in their right mind writes an emulator in Python? Yes, we got to talk. So I don't know how many of you were in my talk last year. Probably most of you went away because they realized the catastrophe that was. But I wrote an emulator for ARM, and then I described it for the first 15 minutes without slides because we had technical difficulties. Emulation in Python it's mind-boggling, but it's easy. You set up fake memory. You set up fake processor-like things with registers, and you write code that executes or emulates what the machine would do to the fake memory and the fake register CPU state stuff. It's actually pretty straightforward. I was floored at how straightforward it was, which is why I still love to do it. Again, why would we do it? Because with an emulator, a lightweight emulator, you can answer questions about code very quickly and easily. Differently than from symbolic analysis, but equally as powerful and combined as the best. And you can visually walk through code. So a lot of embedded systems don't give me debug access, or I have to go buy a developer's kit that might be close enough to the chip that I'm hacking there from, whatever. If I can throw the thing into a lightweight emulator, and with a little bit of help, just kind of single step through and watch what code does. Just basically recreating the behaviors that a chip does. So let me introduce you to my little friend. Nobody. Okay, a couple of you. But who under 40 got that? Really? All right, cool. Very good. So this is it's a shitty-ass thing that I wrote, but it's so powerful because it's easy and it works. Basically, it just spits out what the emulator has as the registers and the values in the registers, highlights what changed since last time, and gives me the next instruction and lets me hit enter or enter a couple commands that allow me to modify or do things on the fly. Simple, stupid, but it's so powerful. It's like GDB, but without requiring that the processor support debugging. So writing an emulator is a lot easier than you might think. Vivisect provides an emulation framework where you just create an emulator for a particular architecture, like PowerPC. And after setting up some stuff that is generic for most processors or maybe specialized for yours, you create function definitions where the name is I underscore and then the mnemonic that you're emulating. You write a function with that name and attach it to your emulator object, hand in an operand or an opcode, and then you just do to the emulator, which is handed in as the self or the first option, the first argument. And then you do the thing that the processor would do. This is a branch to the CTR register with link, which means it's a call. With link just means store where we're at and we're going to return here. So we say the next address after this one is the current address plus the length of the opcode. Simple, okay, right? We then get the value of the CTR register, the counter register. We then set the link register to the next virtual address and next VA. And because of the way the emulator works, if you return a value from this function, it will take that as a jump and it'll make the program counter end up at that returned value before executing the next instruction. So we just return the counter. How easy is that? Even more important, how fun is that? I didn't think that writing a processor emulator could be that easy and simple, but it is. Okay, let's take something a little bigger, a branch conditional. Okay, so PowerPC is a pain in the ass. I may have mentioned that. They have about 3,000 branch instructions, including things like decrement the counter, and if it's 0, and the true bit is set, and with link, and like they've got all these different gargantuan named branch instructions. So here's the branch, decrement, not 0, and false flag. Who makes this shit up? Start off, hey, you know, if we don't have 2 operands, print an error message. Then get the counter register, decrement it by 1, and then write the counter register with a new value. If it's 0, return, because we're not going to branch. That's the not 0. If the first operand is true, or is non-zero, then also return, because this is the false on the end. If we've made it through that craziness, return the value in operand number 1. Remember, we're 0-based. 0 and then 1. And what does that do? That says, make the program counter point to whatever was in the operand index 1. A little crazy, but it's PowerPC crazy, not writing an emulator crazy. And actually, I find that kind of refreshing because it helps me understand what all those stupid, crazy assembly instructions mean. I mean, you can read through it, but you learn it much better if you write a disassembler for it or in an emulator. So we did bring in a hardware debugger. And what this looked like is this piece of equipment right here. We call it noisy because it's like sitting, listening to a jet engine all day. But it's NXP's server 1U rack-mounted module. Why do I care? Why do I want that? Well, it's running Linux. So I actually get into GDB, and I attach to whatever process, or I start up whatever process, and I just write stuff into memory, and then I execute it, so I can make sure that what happens on the real hardware is what happens in my emulator. It turns out there are some very interesting things, lamentable things, about NXP's documentation style. Like, what is bit 0 to you? Is it the most significant bit or the least significant bit? What's that? It's the least significant bit in any sane documentation written by human beings. This was not any of that. So we start everything with bit 0 being the most significant bit. Oh, by the way, it's a 64-bit operating architecture design that is made to be used as a 32-bit architecture as well, like for cheapo things. And a lot of the instructions are literally take bits 32 through 63, the least significant bits, and do these things with them. It's like, would you just please get with the program? Anyway, we found several bugs that were class-oriented like that were easy to fix, but only because we were able to use hardware to make sure that what we thought was going on was really what was going on. You guys got some brain power left? No blood dripping out yet? Okay. I see like more than 3/4 of you have stuck with me. Thank you. I think people have actually come in addition to leaving, and that's totally cool because this is really thick, gritty stuff. Symbolics. Let's talk about symbolics a little bit. I said before that symbolic analysis is the art of breaking down assembly instructions into their symbolic effects, like push EBP for Intel architecture, right? What's that do? Well, it decrements the stack pointer by 4 or 8, depending on the system you're on, 32-bit or 64. And then it writes the value from EBP into the memory location pointed to by the stack pointer, right? Those are the actual effects of the push EBP instruction. Does that make sense? Didn't lose anybody, right? Okay. Symbolics basically says, if I've got the push instruction, do the push things, and spit out a list of symbolic effects. Okay, really magical word, Atlas. Great, thanks. What is symbolic effects? Well, I'll tell you. We wrote a bunch of Python objects which represent operands like registers and memory dereferences, or memory operands. And we wrote a bunch of operators like equals and less than and subtract and multiply and all the things that you would do in a computer system. Turns out, in a loose sense, a computer system is just a really powerful math machine. So the majority of code that has been written can be reduced to algebraic minimums. Now, I'm not going to go down that road because using jargon doesn't make anybody happy. But basically, I can say the effects are these objects, and then we use the magic of Python to allow us to overload all of the mathematical or the algebraic functionality built into objects. So when we say we have an object here, we say x equals some a constant object with a number 4. So it creates a Python object, and it knows that it's the number 4. And then we say that variable plus constant value 8. And because we've changed the actual plus handler for each of those, one of them gets called and the other thing is handed into it, and it's able to spit out an add operator that has both of those two things as its children. So we end up with a symbolic tree of objects that as we just do mathematical things to them, like add, subtract, multiply, divided, we end up having Python just track the state and what it was all the way through. Now, we do have code that says solve, and it'll go, as long as there's nothing that's not solved, it'll go through and it'll add everything up and it'll go, boom, there's your answer. Now you'll see a directed graph on this slide. That's not symbolics. But if you try to do symbolics without using a directed graph, you'll be very limited. So Vivisect wraps in a directed graph library. We won't get too much into that right now. But basically, we select a path of code. We translate all of the instructions in that path of code into their symbolic effects, which I like to call simple symbolic effects. And then we end up with a list of symbolic effects. We run that list of symbolic effects through a symbolic emulator, and it says, oh, I've got all these, hey, EBP is this, or, whatever, and it stores in the emulator the register state or things, we don't even call them registers, they're just things. And so when we do a function prologue, you guys know what a function prologue is? It's the first couple instructions that a compiler will almost always put at the beginning of a function. like push EBP, move ESP EBP, right? That's a x86 32-bit function prolog. Very, very common. We'll talk about that in a minute, what that looks like. But as we extrude through there, instead of we say, I'll walk you through it real quick. Push EBP. So we subtract 4 from the stack pointer, and we put EBP onto the stack, in the memory that the stack pointer points at. Then move ESP into EBP. So the simple effect is we set EBP to the value of ESP. But when you start to extrude state data through this code path, that second instruction, once we emulate it, it turns into an applied symbolic effect, where instead of putting the value of ESP into EBP, we end up putting the value of ESP minus 4. Because ESP has been modified from the beginning state. And the emulator knows that. A little bit of PowerPC assembly. Your brains aren't melting yet. Good. Okay. No emergency rooms here today. So this is a PowerPC set of assembly instructions. Store, write back, update, blah, blah, blah. This is basically push EBP and move ESP, EBP in PowerPC parlance. So, and we're going right here, we move from the special register called the link register, and we put the value into register 0. Okay. And then we store blah, 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 blah. Okay. So you don't have to know PowerPC assembly to know that these are PowerPC assembly instructions. Can you see that at all? So what we've done here is, here are your instructions that we just looked at. The simple effects of these instructions convert to write memory. The location of memory is subtraction of variable R1 minus hex 10, and it's 4 bytes in length, 32 bits. And we write into that location the variable R1. So we've written to memory. We then set variable R1 equal to add R1 plus negative 16. Okay, this is a little lame, but it works. That is actually following what the pseudocode in the PowerPC manuals say to do. I would have personally chosen to use a subtract, but hey, want to keep really close to what the documentation says. Then we set variable R0 to the link register variable. Okay? So simple effects here. Write memory, the location is the addition of R0 plus hex C, or 12, added together. 4 bytes in length. The value of R31. And then another one, write memory, the addition of variable R1 plus hex 14, size 32 bits, of the value R0. Now, you'll notice, R0 has already been updated to be the link register here, right? So in simple effects, we don't care. Just boom, 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 boom. These are the things the processor has to do. Once we apply them, however, we have applied effects, and they're all actually the same effects until you reach this one right here, write memory, the location of which is R1 plus 4, and make that equal to the link register. Starting to see why I think this is very powerful? Does it make sense? It doesn't have to make total sense. You don't have to be a guru yet. That'll come later. Symbolic also has what we like to call pretty output. So this is the verbose output. We made the verbose output something that if I literally copied and pasted this into an interactive Python interpreter, it would regenerate the state. Loves. But the pretty output is, hey, R1 minus 16 equals R0, or R1. R1 equals R1 plus negative 16. R0 equals link register. R1 plus negative 4. So R1 minus 4 equals R31. R1 plus 4 equals link register. R13 plus this constant is red because it doesn't do anything, but it wants us to keep track that we did a read here. And then R12 is the memory read of the location R13 plus this thing, 2 bytes in length, 16 bits. This is just the representation, just the printing of the state for ease of working with it. But I end up having the entire programmatic state stored so that I can roll through and say, what's the last thing that was put into R31? And I just start at the end of the state and go up, boom, boom. Oh, and R31 was set here. It has this full symbolic state. I can reduce it to the very simplest of function things like the plus 4, minus 10, blah, 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 all collapses into one number. Or I can look through and say, this has had 5 different things done to it. I know how exactly that value is being calculated, which tells me actually a lot about what the compiler was doing, which helps me figure out things like we're adding some arbitrary value to memory, to a piece of data that I handed in as an attacker, and that is being handed into malloc win. Why is that a win? Anybody tell me? Because it's a finite number system. If I hand in data that I control, and it's added to or subtracted to by some number, if I have enough control, I can have an underrun where the number gets very, very large, or an overrun, which means the number gets very, very small, in which case malloc returns too small of a value, or a piece of memory, for the thing that's going to be written to it. And from there, we've got a heap overflow. Writing Symbolic's translator code is actually probably a lot easier than understanding all the stuff that I just dumped on you. So this is going to go really easily. Again, in the same fashion as the emulator, we write helper functions that start off the symbolic translator is what we call this. If you create a function with an I underscore, that's an instruction. So I add IS, which is add in immediate shifted. So we shift it 16 bits. But it's a little different way of thinking. Because remember, we have to return a list of symbolic effects. We can't make concrete use of data. Like in an emulator, we could say, give me this flag value. And if it's this flag value, then I want to go this way. And if it's the other thing, then I'll go this other way. No. You have to think in terms of actual just symbolic effects. So addis, the source 1 is the the operand object number 1 in the instruction. Source 2 is the operand object 2. Source 2 is then shifted left, constant of 16. And we have to hand in, because it's a concrete number system, the numbers can only be an actual size. It can be 16 bits, 32 bits, 64 bits. So we track that throughout the state because it's important, it's valuable. So we shift source 2, this operand number 2, which is a symbolic object, by the way, it's not a concrete number. We shift that by the constant 16, and then we sign extend it to the right size, just making sure that it's all tracked in state. We then add the result. Now, source 1 is a symbolic object. It's probably a constant in many cases, or a register value. And so we end up with an O underscore add object with source 1 and source 2's symbolic objects as children. We then set that back to operand 0 the result. Over here, on the right, if you can see it, we've got an effect set variable function, an effect read memory, effect write memory, effect f of x, which is a way of reducing a function call, and EFF constraint. So let's see, if we go, this is going to generate an EFF write memory. It's going to take in the symbolic address, the symbolic size, and then the object that's going to be written there. And we just add to the effects log a write memory object, and we hand in the virtual address, the symbolic address, because we want to track for troubleshooting and other things. We want to track which instruction created the symbolic effect. So we store the VA, current VA virtual address. Then we store the symbolic address that we're writing to, the size that we're writing to, and then the symbolic object that we're going to be writing there, and we track that. That is a lot to digest. And if nothing else, you've come away with the fact that I'm way too nerdy for my own good. Hopefully you've been entertained. I do want to give a few props here. The NMFTA, the National Motor Freight Traffic Association, a conglomeration devoted to cybersecurity of heavy trucking, they gave us funding to work on this project because it's in their best interest that we have good tooling to find bugs and make good use of, kill them, right? They also, they funded us, they also connected Grim with NXP, and then we created a partnership and did cool stuff, and they kept us on task. They're like, can you send me a status update? Yeah, keep asking me in 2 weeks. Okay, can you send me a status? Thank you, yeah, sure. And thank you for NXP. They provided us hardware and tech support on how to get the hardware working. And then a few things that are next. We're just going to continue to enhance it, and hopefully it will be merged into mainline Vivisect within the next month. It takes a long time when you got that much code. So you can get access to it right now at my GitHub, GitHub Atlas of Doom with zeros Vivisect. In the NV_PPC branch, PowerPC branch, I should have that merged into the Atlas merge branch, which is what I recommend people use most of the time anyway. And then when it gets merged in, it'll be in the actual Vivisect repo. Thank you very much. I appreciate your indulgence, and I hope you were entertained and educated.